Hi everyone, my name is Junlin He. In this video, I'm going to present the paper BSPNet Generating Compact Meshes while Binary Space Partitioning. So this paper talks about how to generate 3D shapes from 3D data using deep learning. The authors of this paper are inspired by a popular 3D data structure, which is called BSP tree, and they adapted this technique to teach the neural networks to learn the shape of a 3D object. Before the work of this paper, all prior methods, they learned the shape indirectly. We know that to represent a 3D object, the most common way is to use polygonal mesh. So what is a polygonal mesh? A polygonal mesh is a mesh which is comprised of polygons, as you can tell from its name. And as you can see in this picture, if people want to represent a 3D dolphin, then they will use a dolphin-like mesh. And if people want to represent a 3D train, then they will use a train-like mesh. However, prior to this paper, to represent a 3D object using polygonal mesh, the conventional methods, they don't learn the mesh directly. Instead, they learn voxels or point clouds or other things. After that, they will transform the learned voxels or point clouds or other things into the polygonal mesh. So you can basically think about this process as a two-stage learning process. So the first stage learns those intermediate representations. Then the second stage transforms those intermediate representations into the final polygonal mesh. So the main reason why those methods they don't learn the mesh directly is because the irregularity and the uniformity of the polygonal mesh do not naturally support conventional convolutional operations. In contrast, different from prior works, the BSPNet, which I'm going to talk about in this video, it learns the polygonal mesh directly. It doesn't learn voxels, point clouds, or other intermediate things. Therefore, it's a one-stage learning method. The authors of the paper claim that their one-stage learning method has several advantages over other two-stage learning methods. One advantage is that it has higher computational efficiency since it doesn't need to extract the isosurface from data. It requires less computation. Another advantage is that their method has better visual quality. Specifically, it can represent the sharp geometric details of objects well, while others cannot. For example, to represent this table, as you can see in the picture, the BSPNet successfully shows the sharp corner of the table while the other one does not. By the way, a voxel is basically a single data point in the 3D space, as pixels are the building blocks for 2D images. Voxels can also be the building blocks for 3D objects. So voxel is actually very similar to the pixel, except that one exists in the 2D space while the other one exists in the 3D space. As I said before, some other methods learn voxels first and then using the learned voxels to generate the polygonal mesh. While this BSPNet, it does not learn values for voxels, it does use voxels as their training data. So how does this new method learn the polygonal mesh directly? How does it work? Let's take an example. Let's say we're given those voxels as training data. We try to reconstruct the shape of the cube in the picture. So we are not given this shaded cube directly. The shape of this cube is what we are trying to learn. So we are only given those voxels with labels. The voxels inside the cube have label 1, while the voxels outside the cube have label 0. I have colored those voxels differently using red and blue. So now, given those label voxels, we try to reconstruct the shape of this cube in the space. As you can see, this is basically a binary classification problem. We want to separate the space into two subspaces so that voxels with different labels can be separated correctly. Recall that in a simple 2D binary classification problem, we are given some data points in the 2D space with different labels. Some points are labeled with labeled 1, while some other points are labeled 0. We try to draw a line, whether it's a straight line or a curved line. We want to separate this 2D space so that points with different labels are separated as best as we can. So the 3D space case is very similar to the 2D space, except that instead of finding a line, we're now trying to find a 3D shape to separate those points in the 3D space. And if we can successfully find this shape, then we actually have successfully estimated the original 3D object's shape. So using this observation, the problem of reconstructing the 3D object's shape can be turned into a binary classification problem. However, using this observation is not enough to get a polygonal mesh of the object, even though we can find a very good function to separate those voxels. In most cases, if we draw the function we just learned, it won't be in the form of polygonal mesh. It's very likely to have some irregularities. So as you can see in the picture, I just draw an example to show this. So in order to get a polygonal mesh, most of the prior methods will use a technique which is called isosurfacing to extract the isosurface of the shape. This method can extract the mesh very well, however, it is expensive. So this is where the contribution of this paper comes into play. To avoid this expensive isosurfacing process and to get the mesh directly from the learn function, the authors of this paper carefully designed the structure of the learned function so that it can be interpreted as polygonal meshes directly. In order to learn the function, the authors of this paper used the neural network. They named it BSPNet. It's called BSP because the structure of the function is inspired by a popular 3D object data structure, BSP tree. So this popular data structure's full name is Binary Space Partitioning Tree. As its name suggests, it recursively divides the space into two subspaces by using hyperplanes as partitions. Each time it adds a new hyperplane to the space, the 3D object will be divided into smaller parts as a result. So I will use this picture to explain the idea of the BSP tree. So this example is actually taken from the paper, and it's actually a 2D example, but the idea is the same. So we have a triangle and a square in the picture. To build a BSP tree from this picture, which contains a triangle and a square, so first we need to choose a line randomly in the picture. Let's say we choose this line which I have marked it with red. And we use this line to divide the picture into two parts. Then we recursively divide these two subspaces until each subspace only contains a single line. In 3D space, people will usually recursively divide the space until each subspace only contains a single convex set. So as a result, we can represent the shape in this picture as a tree. So this is why it's called BSP tree. It can also be used in the 3D space to represent a 3D object. Since the polygonal mesh can be recursively divided into different convex sets, the authors of this paper therefore proposed to build a function using this tree structure. They use neural networks to learn the convex sets first, and then reassemble those convex sets into the final polygonal mesh. As a result, once the model has learned a good function to separate those points, it has already learned those convex sets. Therefore, the polygonal mesh can be directly built using those convex sets. This is the structure of the BSP net. So its structure can be divided into three modules in terms of functionalities. The authors of the paper used this 2D example to explain those different modules. So the first module will learn different lines in the plane. Then the second module put those learned lines together into different convex sets. Finally, the third module groups those convex sets into the final output shape. Inside the red box is the first module. It uses multi-perceptron layers to transform the learned feature vector into parameters of p-planes. So the feature vector is an output of a pre-trained encoder. For 2D images, the authors use a simple 2D convolutional encoder. For 3D objects, they use 3D-CNN as their encoder. So the first module takes the feature vector as input and outputs p times 4 numbers of values, which represent the parameters for p-planes in the 3D space. So the p here is a hyperparameter. It's the maximum number of planes that can be used to build the final polygonal mesh. And 4 here represents the 4 parameters A, B, C, and D of a 3D plane. So we use a capital P to represent the matrix of this plane's parameters, and we use X to represent the matrix of the training data points. Then we do the matrix multiplication. Of course, in order to do it successfully, we need to use X to multiply with P transpose. Then we got a new matrix D. Its dimension is n times P, where n represents the number of data points in the training data, and the P represents the number of planes. So this matrix D represents the signed distance from each point to each plane. The second module then multiply the matrix D with a new matrix T. So this new matrix T is the parameters we need to learn during the training. It's intended to be a binary matrix and is responsible for choosing the right candidate planes to build the convex sets. Therefore, after the training process, we want the matrix T to be as close to a binary matrix as possible. In other words, after the training, we want each of the elements in the matrix T is either very close to 0 or very close to 1. In order to achieve this goal, the authors of this paper use a loss function, which I have shown here during the training. By minimizing this loss function, the elements of the matrix T would be pushed to either 0 or 1. As a result, the planes which we have learned in the first module will be grouped together into different convex sets. Another important contribution of this second module is that it also helps the model learns whether a point is outside or inside a convex set. In the 3D space, if we have a convex, we can set a direction for this convex. So after we set the direction for this convex, then we say that this point is outside this convex and this point is inside this convex. The authors use a maximum signed distance value function to tell whether a point is outside a convex or inside a convex. For example, in this 2D picture, suppose we set the directions for the sides of this triangle like this. So if a point is inside this triangle, then it's actually behind all those three sides. So its side distance to all those three sides would be negative. Now suppose we have another point which is here. It is actually outside this triangle. So as you can see, its side distance to this side is negative. And its side distance to this side is also negative. However, its side distance to this side would be a positive number. So we can conclude that if a point is inside a convex, then its side distance to the convex sides would be all negative numbers. But if a point is outside the convex, then at least one of its side distance to the convex sides would be a positive number. So using this observation, the author proposed this equation to tell the point's position relative to the convex. If the maximum side distance to the convex is negative, then it's inside the convex. In contrast, if the maximum side distance is positive, then it's outside the convex. However, using this equation, if we do the training, the gradient would only flow through one plane, which has the maximal distance value. Then the whole training process would be kind of problematic. To relieve this problem, the authors then propose another equation to do the basically same job. So instead of observing the maximum side distance to a convex, now they applied a ReLU operation on the side distance matrix D. Then they add all the side distance values together. To see how it works, consider what happens after applying the ReLU function on the side matrix D. The ReLU will put all negative distances to 0 and keep all positive distances. For example, for this red point, if we do the ReLU, then all its side distances will turn to 0. Adding them together will still be 0. However, for this point, which is outside the convex, if we do the ReLU and then adding all distances together, the summation would be a positive number. So during the early time of training, there might be several side distances are positive. So the gradient will flow through all those planes, and the training process will be better than before. Then, after those first two modules, we have the third module. Instead of learning whether a point is outside a convex, now the model tries to learn whether a point is outside the final polygonal mesh. The authors proposed to use the mean pooling to do the job. So here is the equation they use. This Cjx is the distance between a point and a convex set, which the model has learned in the second module. So for a certain point, this equation finds its minimal distance among all convex sets. If it's a positive value, then it's outside all the convex sets, which also means it's outside the final polygonal mesh. However, if the minimal distance is 0, then it means this point is at least inside one of the convex sets. Then it means it is inside the whole polygonal mesh. So the author still use this 2D example to do the explanation. Suppose we have a point here. As you can tell, it is outside both two convex sets. Therefore, its distance values to these two convex sets are all positive. As a result, its minimal distance is a positive number, and this minimal distance also represents the distance between this point to the whole mesh. Now consider this point. It is inside the square. Although it is outside the triangle, its side distance to this triangle is a positive number. However, its side distance to this square is a negative number. After the ReLU operation, this negative side distance will turn into 0. So as a result, its minimal distance to those two convex sets would be turned into 0. So therefore, using this minimal distance, this equation can tell whether a point is outside or inside the whole mesh. Again, to help training, the authors of the paper propose another equation, which is shown here. Notice that in the training data, if a point is outside the shape, the true mesh, then its label y is 0. Otherwise, if it's inside the shape, its true label is 1. Therefore, when we get the minimal value from the third module, if it's a positive number, which means it is outside the mesh, then we need to transform it into 0 in order to match the true label. If it is 0, which means it is inside the mesh, we need to turn it into 1. So this is why the operations in these brackets is written in this way, instead of putting the Cjx directly into the brackets. And this 0, 1 means doing the clipping. If the value in the bracket is less than 0, then no matter how small it is, we set the value to 0. And if the value is bigger than 1, and no matter what positive number it is, we set it to 1. This Wj here means to do the weighted summation. So this equation basically does the same job as the equation which we have seen before. By the way, this Wj here is also the parameters that the neural networks need to learn during the training. So this is the structure of the whole model. To do the training, the authors use the loss function as shown below. So as you can see, this W and capital T, capital W are all matrices of parameters that the networks need to learn. So this W here is the parameters in the first module which describes the p-planes, and the T here is the parameters which is used in the second module to group planes together into different convex sets and to tell whether a point is outside or inside the convex set. The capital W here is the parameters used in the third module to tell whether a point is outside or inside the final polygonal mesh. So the whole loss function is comprised of three loss functions. The first loss is basically a plane mean squared loss function. It is used to measure the difference between the predict labels and the true labels. And this f given xg here represent the true labels. And the second loss, LT, can be written like this. So as we said before, it pushes the value of elements in the binary matrix T to either 0 or 1. And the third loss functions, it pushes the Wj as close to 1 as possible. However, the authors find that after this training process, the outcome is not satisfied. So this is what their outcomes look like. So in order to improve their outcome, they devise a second training phase. They use these two equations which we have seen before. Remember, we do not use these two equations during the first training process, since the gradient will only flow several planes and the result can be problematic. However, these two equations are actually more accurate in describing whether a point is inside a convex set or a mesh. So after the first training process, we do not worry about the gradient anymore. The authors use them here to refine the results. In order to use them, the author devises a new loss function which is different from the prior one. As you can see, it is comprised of two parts. The first part can be written in this way. All it does is to pull Sx towards 0 if the point x should be inside the mesh. Otherwise, it pushes Sx beyond 1. Also, to minimize the overlapping of the learned convex sets, the authors propose to use this second loss function. They first calculate a mask M such that mxj equals to 1 if x is in convex J and x is contained in more than one convex. After the second training phase, the authors showed that their outcomes does improve and is much better than before. So that's it. This is the whole picture of the model. The authors of this paper explain their idea using a 2D example, but the idea is same when it's being applied in the 3D space. The authors of the paper claim that their work can be used in various tasks, including auto-encoding 2D shapes, auto-encoding 3D shapes, single-view reconstruction, etc. Here are some comparisons of their method with other state-of-the-art methods. To measure the performance, they use several metrics, including chamfer distance, normal consistency, and light field distance. Here are the reports of different methods' performance under various metrics. The best results are shown in bold. The authors show that their work outperforms other methods in most cases. So, to conclude the contribution of the paper, the authors argue that their method is the first deep generative network which directly outputs polygonal mesh without needing to do the expensive isosurfacing work. Also, their results show superior visual quality. Lastly, their method can be used in various tasks. In terms of the limitation of their work, the authors said that their BSPNet is only good at decomposing a shape into convex sets. For objects which naturally have concave shapes, their work cannot represent those objects very well. Also, they mentioned that the training time is quite long. They spent 6 days for 4,096 planes and 256 convex for the SVR task across all categories. To improve the model, the author suggests that in the future, they might do some architecture change to the network in order to address their shortcomings. So that's my presentation for this paper. Thank you for watching this video. Thank you for your time.